We've talked about distances and measuring them in the universe. Now let's talk about just the age of the universe, this concept of cosmic time. So, like I said before, the observable universe is 93 billion light years in size. And we all live in a universe that is 13.8 billion years old. Well, some of you might be questioning, wait, doesn't that not add up? If the speed of light's the ultimate distance, the universe is 13.8 billion years old, then shouldn't the photons only be 13.8 billion light years away instead of this 93? Well, turns out it's a complicated problem, and it turns out what the universe has been doing is expanding in size. I always like to think of this as this explosion that happened at the Big Bang that's just throwing material out there. But that analogy breaks down. If I want to talk about, say, a grenade blowing up, grenade is a bunch of energy concentrated in the center, and when it's ruptured, it makes fragments of material that gets thrown out as projectiles. The universe isn't a big grenade. The universe itself is what's expanding, explicitly that space-time quantity. So the universe was this singularity right at the moment of the Big Bang, and space-time itself is exploding outwards. Strange, I know, but that's what's happening. It's space-time itself that's going out there, and the rate that it's going out is increasing. So, going back to the hand grenade analogy, it's kind of like having an explosion here, and yet somehow the further away the shrapnel gets from the explosion, the faster and faster it goes. That's what we see in the universe. As the universe gets further and further away from us, it's going faster and faster. So yes, the age of the universe is 13.8 billion years old. But the size of the universe has ballooned to this massive, gigantic size. So what we're going to do now is go through the time scales of the universe, the ages. Right? We'll do this divided into 5 stages. We're going to start off with the very early universe, the very beginning of time itself. And then we'll talk about the early universe, and start to get up to the dark ages. So you'll find that time is going to be very, very short initially. Our timestamps will be very small time steps, and each step will be subsequently longer and longer as we go through ages. So let's go to that very, very early universe. I mean the first picosecond, 1 times 10 to the minus 12 seconds after the Big Bang. So some things we need to emphasize here. The concept of time before the Big Bang doesn't make sense. There is no before the Big Bang. And I'm not trying to be philosophical here. I just mean as a scientific fact. There is no definition of time before the Big Bang. Remember, time is wrapped up in our concept of space-time. Right? It's all one quantity. When the universe was that singularity, there was no space-time. So we can't define a time before the Big Bang. It's literally physically impossible. So, the Big Bang, whatever you want to call it, the Big Bang happens. And now we're going to look at the universe, how the laws of physics change in that picoseconds after that. What we do know is that small fluctuations in the universe right after the bang, little discrepancies. Maybe there was a fraction of a tiny bit more photons here, just a little bit more density over here, and this not quite singularity anymore. Maybe a little bit bigger than a nucleus of an atom right now. Right? Small little discrepancies there have created these cosmic size consequences. We literally will see maps of bundles, fibers, connecting the galaxies. how the different galaxies are tied together by these strings here. And our understanding of the universe is that it's due to the fluctuations at this very, very first fractions of a second of the universe. Furthermore, this is where the fundamental forces first start to come in existence. Less than that picosecond timescale, and the forces don't exist yet. The energies of the universe are too high. The universe is too compact for these fundamental forces to have any meaning. But as the universe started expanding in size and cooling down, the fundamental forces start to emerge. A reminder, that's our gravity, electromagnetism, the nuclear weak force, allows for radioactive decay, and the nuclear strong force, which is what holds nuclei together. These four forces finally condense out of the hot soup of the early universe. So we go into the next stage in the universe, and this will be from about 1 second after the Big Bang to a couple 100,000 years into the life of the universe. So at this stage, the very beginnings, there's going to be just a very hot universe. You're going to have gamma rays coming together, hot, like I said, high energy, hot photons. They're going to be interacting, and what'll pop out of that are matter, antimatter, electron, positron, right? And remember, matter, antimatter, they tend to smack into each other and collide. Right? They're electrically charged objects. They feel attractive forces to each other. So those matter, antimatter particles will come together, annihilate, and then re-emit gamma ray photons. So at this stage in the universe, there's not even stable matter sticking around because it's spontaneously created. It'll be spontaneously created, and then it'll spontaneously annihilate with antimatter. And this process will just keep going and going. But 2 facts. Fact number 1, the universe is swelling in size. So these particles are getting further and further away from each other. That means the universe is cooling down. The rate of these reactions is going to go down. Fact 2, we know this for a fact, but we do not know why. Something caused there to be just slightly more matter in the universe. We know this because, well, I'm talking to you right now. We're all composed of matter, right? Our studies of fundamental physics, we know that matter and antimatter are created at equal rates, which means that they'll annihilate each other equally as often. Yet something about the universe at this stage caused there to be an abundance of matter. There's a lot of speculations what caused that, but what we do know is that we're made of matter. So this is a very much open-ended question in astronomy and cosmology right now. We'll keep going, right? Get past those initial seconds, start to get into the first few minutes of the universe. No, huge steps. And at this point, nuclei can finally start condensing, right? There'll have to be protons and neutrons, and they're going to start forming isotopes and some helium as well. So the universe is cooling off, right? And getting bigger again. So after these first few minutes, somewhere between these first few minutes to the first 100,000 years, that's when finally the universe is cooled off enough that electrons can be bounded to protons, right? And this is going to be a crucial, important step for this. We'll talk about this in future videos. At this stage, the light of the universe starts to become clear. We're able to start seeing this universe at this age. Everything before this, we've pulled out from our understanding of theoretical physics. But evidence for this stuff gets capped off at this stage here. And this will be the source of what's called the cosmic microwave background radiation. Basically, these atoms here, as they cooled off, they're radiating photons trying to get to their lowest energy state, their ground states. And those photons are still with us today in that CMB. Well, now the universe is growing in size and getting older, more mature. And so during the next couple 100,000 years to the first billion years of the universe, that's when the first stars are going to start forming. We call this the Dark Ages because during this time, all we have is this sea of helium and protons, all right, helium and hydrogen. And the only photons from this time were from them cooling off. And those photons are part of the cosmic microwave background. There's no stars generating new photons in the universe. So it's only after about 200 million years that the first stars start to form and new light gets to be introduced to the universe. And I'll keep waiting. Right? The first stars, our sun's probably a third generation star. We get to are now 13.8 billion years. So as a recap, right? You have the earliest eras of the universe, and as time keeps going, right? As we get closer and closer to the present, the temperature of the universe is going down and down. Right? So, a big theme will be, well, what happens into the far futures of the universe? Will this trend of the temperatures going down as the universe gets bigger continue? Right? And my answer to that is, let me elaborate on that. All right? Obviously, we see how the universe looks today. We can calculate when things happen and what events had happened during its lifespan, but we all want to try and predict the future. We want to see where the universe is going to be. But it's a very difficult task. Specifically, the fate of the universe, what will happen to the far futures universe, it depends on the critical density of the universe. So what you're looking at here are plots of basically age of the universe, right? And this is our current time. So past, future. Right? And you have to take into account, we're going to look at the age of the universe and the average distance between galaxies. Basically, how spread out is the matter in the universe. And the crucial factor is this omega m. It's called the density parameter. What this thing is, it's a dimensionless number. It's the ratio of the density of the universe. Remember back when we talked about the interstellar medium, how many atoms per volume exists, right? So this medium is the actual density of the universe over the critical density for all these different inflections to happen. Right. And our current estimates have the critical density of the universe at about 5 atoms per cubic meter. Right. So let's start piecing this here. This yellow line here, right? That is if the density of the universe is exactly equal to that critical level, that critical density. If we go slightly above that critical density, right, that'll go down to this blue region. If the universe is slightly denser than that critical value, well, look at the separation. Look at this curve here. The universe will continue expanding for a little bit, and then the galaxies will start coming closer and closer and closer. Now, of our critical densities in the red region, we are less than, if the density of the universe is less than that critical value, then we'll see the distance between the galaxies continue to grow. The rate at which they grow will be different and now lead to slightly different conclusions on the ultimate fate of the universe. But the fact is, knowing this omega, this density parameter, the better we know this number, the better we'll be able to predict what happens in the universe. Because the ultimate fate is dramatically dependent on that. Here is just a couple of cases here. Right? If the density is greater than that critical value, if it's too great, you'll get what's called the Big Crunch. The universe starts off at a Big Bang, blows up in size, and then gravity takes over and just crushes everything back to the center. and probably to birth a whole new universe. And you could speculate that universes go through this secrets of this oscillating behavior of blow up, do a bunch of interesting stuff, and collapse back down and blow up again. But that's purely speculative now. By definition, whatever comes after this, and after I do mean quotes here because time ceases to make sense anymore. Right? So the universe could crush back in itself. What it could do is just reach a point where the universe has blown up, and then it's static. Nothing's changed anymore. It doesn't grow in size anymore. Galaxies are going to be relatively stable around each other, but they'll eventually cool off and die. There's no new source of hydrogen. Another one's called the coasting universe. What's happening here is that the universe is blowing up in size and steadily increasing, but at a constant rate. It's basically the distance from us to another galaxy will continue to grow with time, but it will be the same rate of getting further and further away from us. The last case, if our density parameter is less than that critical value, is called the Big Rip. The universe is going to blow up from the Big Bang and keep going faster and faster and faster. So fast, in fact, that the universe will literally tear itself apart. The expansion rate will go so incredibly fast that atoms will literally be torn apart because of how quickly space-time is just growing in size. And that's what we call our Big Rip. Our evidence today, our best evidence, points to what we call a flat universe. I won't elaborate further on that today. I'll say we live in a flat universe. That means that the density of the universe is, to the best of our knowledge, exactly at that critical level. Which means that our universe is going to live for an incredibly long time and die of what we call a big freeze. All the energy will be so far apart, so spread out, that nothing stable will exist anymore. Even the black holes will decay away and just throw all their energy out into the cosmos. And at that point, the entire universe will just be this loosely held together sea of photons, because all the matter will have just decayed away. So with that, we'll call it in section 19, and we'll see you all next time.